Hello and welcome to this course. I am Dr. Sriram Kumar. Today we are going to learn glass transition temperature. Glass transition temperature is very important properties of a polymer. And based on glass transition temperature, we can control mechanical properties of a polymer. So now let's understand the types of the polymers. First, as we had discussion about the types of the polymers based on the structure, we have amorphous kind of this polymer. So in amorphous polymers, the position of a chain is not fixed. For example, in this case, we don't have this fixed position. So maybe the polymers may be anywhere. So because of not fixed position of the chain in this polymer, it has a distinct properties as compared to the crystalline polymer. So if you have the crystalline polymer, then you have this kind of the ordered structures and that kind of the polymer is called the crystalline polymer. But in real life, we have semi-crystalline polymer in which we have this contribution of the amorphous polymer and in the crystalline polymer, so that we will have the some section in that polymer is this in amorphous and the crystalline. So we have this is the kind of the ordered structures. So we have ordered structures and these are the kind of this random structure random structure of the positions, and that's what is called the semi-crystalline polymer. So we have glass transition temperature for amorphous polymers only, and the semi-crystalline polymer has glass transition temperature and melting points as well. And if you think about what is a crystalline polymer, so for the crystalline polymer we have only melting point, not glass transition temperature. So now let's understand what is glass transition temperature. As we had discussion here about the amorphous polymers. So for example, if we have the amorphous polymer in the liquid state, and if we just cool down that polymer, what will happen? Suppose we have this bigger here and we have this polymer there, and if we cool down this one, what will happen? So because of this cooling, since the position of the chain is the random, so even though if we cool down this polymer, we have the position of the chain is frozen, and because of the frozen position change, even though in the so suppose this is in the liquid state and this is in the, so if that cool down, so that is in the solid state. So even though in the solid state the position is not fixed, and this is we can call this is specific kind of the term, that is the frozen kind of the things here, and that's why this is called the glassy state, and this term is called the glassy state. Glassy state. So as we take the example of the glass is kind of this frozen of the liquid glass. And that's why the glass window we see, so that is the in the liquid state. That is not the solid. If you just type on this Google or maybe the YouTube and see the liquid state of the glass, that's really viscous in nature. And if it is cooled down, so there is certain change in the temperature, and because of that liquid just frozen to that the same and that random position, and that's what this is called the glass. So similar thing happened for the polymer. So for this amorphous polymer here, amorphous polymer. Same thing happen as the glass. So at a low temperature, so at low temperature, what happens? That kind of the polymer is a kind of the glassy state, or maybe there's a frozen of that glass. So if you see here, so 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 here this is the first curve is for the amorphous polymer. So now let's understand this first one. So at very low temperature, so here this plot is between the temperature versus a specific volume of that polymer. So if we monitor the change in the specific volume with temperature, so at very low temperature, in this particular temperature, the amorphous material is in the state of the glassy state, that is in frozen form. And when we increase temperature slowly from here to there, so at that particular temperature, that glassy state of that amorphous polymer, glassy state, so that becomes as a rubbery state or rubber-like structure. So this phenomenon occurs at temperature to a certain temperature, and that temperature is called Tg. So temperature at which the amorphous polymer, the state, glassy state becomes the rubbery state, is called glass transition temperature. So at this temperature, so that becomes here a rubbery state. And if you further increase temperature, so what will happen? So this range is the rubbery state, and if you further increase temperature, so here that becomes as the viscous liquid, and for the if you increase temperature, so that becomes viscous liquid. Okay, so now we understand what is the amorphous, what is the transition happening in the amorphous polymer. And we have other kind of the polymer. So this curve is for crystalline polymer. So in the crystalline polymers, since the position of the chain is the fixed, and so in that case we don't have glass transition temperature. So for crystalline polymer, we don't have Tg values. So it only is the Tm, or the melting point. So if you just understand this curve here, so if you increase temperature, so at initially that is in the solid state, and if you increase temperature, so that will slowly increase the specific volume, and at a certain temperature, there is fast increase the specific volume. So this temperature is called the melting point temperature. So that temperature, the solid state of the crystalline polymer becomes in the liquid state. So here in the for the crystalline polymer, it changes from solid to the liquid state, or maybe viscous state. Okay, and what about if we have semi-crystalline polymer, for example? So this is the example of the semi-crystalline polymer where we have this some properties of the amorphous polymer and some properties of the crystalline polymers. So for this kind of the polymer, we have something here. So at very low temperature, we have the glassy state. At the same time, it has some solid state kind of the things, solid state, and it has the Tz value, that is the glass transition temperature, because of the glassy state of the materials. And if you further increase their temperature, so here, so this has the contribution maybe from the rubbery state. So at so this is for the rubbery state. And when you further increase temperature, what will happen? There is a increase in the specific volume. So this temperature corresponds to the melting point of that crystalline part of that semi-crystalline polymer. So a semi-crystalline polymer has both glass transition temperature and melting temperature. And so here, these values, here, these TM values can vary from here to the there. So it depends on what is the percentage of the crystallinity. So suppose if you have the high crystallinity nature, so that TM is close to this pure crystalline polymers, and if there is very less crystalline or more amorphous kind of structure, so this TM will lower down. So that depends on what is the percentage of the crystallinity in that polymer. Okay, so now let's understand what are the factors which affects the TZ values. So before that, we need to understand one key point. Suppose if you want to make a chair, or maybe we want to make a polymer chair. So for that, we need to use the kind of the polymer which has very high glass transition temperature. So if we have some cases here, for example, if you take the example here, if that T, so and T is the greater than TZ, what happens? Suppose TZ is 25 degrees Celsius, and the working condition of the polymeric material is 35 degrees Celsius. So what happens here? If you use this kind of the condition, that means this polymer is in elastic in nature. So polymer is elastic. Sorry, elastic polymer, right? Because that working temperature is greater than the TZ. What about if you have the TZ, that working temperature is less than TZ? That means, suppose if you have the TZ is equal to 50 degrees Celsius and you are working at room temperature. That means that polymer will be in the glassy state. Glassy state. And based on this one, we will understand what are the mechanical properties of this polymer. So based on these two factors, we will control the mechanical properties of the polymer. Now let's understand what are the factors which affect glass transition temperature. So glass transition temperatures can be affected, or we can change based on the manipulating two factor. One is the degree of the freedom of interpretation or the mobility of chain, or maybe we can manipulate with the free volume in the polymer. So if you think about the manipulating the degree of the freedom of the internal rotation, so we can consider the backbone flexibility or the stiffness, or maybe we can consider the steric effect of the side group and the intermolecular forces. And if you think about manipulating based on this free volume, then we can either use the molecular weighted polymer, maybe presence of the plasticizers and the cross link. So these are important factors which affect glass transition temperature. Now let's understand one by one. So in summary, if we have, and later on we will explain in details with some data. So if we want to manipulate based on degree of the freedom of the internal rotation, so if we increase the rigid group in backbone, then the glass transition temperature will increase. So this sign shows that there is an increase in glass transition temperature. And if we decrease the polymer, or maybe if you increase the flexibility polymer's backbone, in case there is a decrease in the glass transition temperature. And steric hindrance, so as it if you increase the steric hindrance in the backbone, that means that you are increasing the glass transition temperature. And further, if you increase if you have the polar functionality, for example, if we have this polars group, maybe the OH, maybe the chloride in the backbone, so because of the intermolecular interaction, there is increase in the glass transition temperature. Again, you can increase glass transition temperature based on the dose linking. So these are the based on the degree of freedom, and there's other thing is that is based on the free volume. So if you add some kind of plasticizer in the polymer, so in that case, there is decrease in the glass transition temperature. And if you just play with the long side chain in the plasticizer molecule, so in that case also there is decrease in glass transition temperature. Now let's understand one by one how these factors affect with the data. So if we consider the chain flexibility and the rigidity, for example, here, if we consider here this one first, if we consider this one, we have CH2, CH2, and there is the, so if this is the polymer, polyethylene polymer. So you have this kind of the chain here. So because of the simple chain, there is free rotation about around this bond here. So there is free rotation, and because of this free rotation, it has and flexibility. It has the lower glass transfer temperature 180 Kelvin. And if you just increase or maybe decrease the flexibility by adding the maybe the double bond here. So if you have here CH2, CH, CH, CH2, what happens here? If you, so you have here the double bond. So because of a double bond in the backbone of the repeat unit, so there is less flexibility in the rotations, and because of the double bond formation and chain, and that's why there is increase from 80 to 188, and that can be further increased if you just use here the bulky group here, maybe the if you have the benzene ring and if you have this kind of a structure. So you, as compared to the simpler carbon, you have the benzene is a bulky group there. So if you have this bulky group, so there is the decrease in the internal rotation, and because of that, there is the huge increase in the glass transition temperature, and that can be further increased by just adding the benzene quantity further. So this is all about how you are playing with the internal rotation by by add by increasing or decreasing the size of the repeat unit. So now let's understand the effect of steric effect on Tz value here. So for example, if you think about what is the effect of steric hindrance, so let's take the example. Suppose we have CH2, C double bond, CH and X, and if that polymerizes, so we have here CH2, CH and X, and we have polymer. So for example, if we have X, for example, we have hydrogen and we have CH3. So for this hydrogen, we have glass transition temperature. So we have glass transition temperature 188 Kelvin. And if we have the methyl group there, so we'll have the increase in glass transition temperature 253 Kelvin. So because of just changing from hydrogen, this one to the methyl, there is some steric hindrance in the rotation of this chain, and because of that, there is an increase in the glass transition temperature. And if you want to understand what is the effect of intermolecular forces, so now let's understand with for example, if we have again CH2, CO, and X, and if that polymerizes, and we have CH, and so if this kind of the polymer we have, and here we have the methyl here, here methyl group, and we have chloride and the OH group. So as compared to the methyl group, we have the glass transfer temperature 253. And if we just change from methyl to the chloride, that increase to 354. And that's for the increase, if you change to hydroxyl group, here we have for the increase to 358 Kelvin. So there is increase if you increase the such kind of the polar molecule. So now let's understand what is happening there. Suppose this is the polymer chain, this is the polymer chain, and initially you had only has CS3 and the CS3. So in the CS3, you only had some kind of the van der Waals interaction. However, if you just change this one, if you change this one with, suppose you have chloride, and if you have chloride, so since chloride is more electronegative, so there is delta minus, and you have delta plus, you have delta minus and delta plus in the backbone. And because of these things, we have such kind of the here the dipole interaction. Dipole dipole interaction. So you have the dipole interactions if you have chloride, and if you have the OH, and if you have OH there, so there may be some kind of the hydrogen bonding. And hydrogen bonding is there, and because of that hydrogen bonding, or maybe dipole interaction, the so that will decrease the intermolecular rotation, and therefore there is increase in glass transition temperature. We have another factor that is based on the cross-linking of the polymer and the crystallinity. So glass transition temperature increase in the cross-linking process if you have this polymer chain, and if you have the cross-linking there, and if you're increasing the cross-linking, that means there is very less free rotation and the flexibility in the chain, and because of that there is increase in the glass transition temperature and crystallinity. So in similar, also the strict mobility of these sort of amorphous materials. So it increases TC with increase in the percentage of the crystallinity. If you have the maybe 50% crystallinity, or maybe the 80% crystallinity. So if there is the increase in the crystallinity, that means there is the increase in the ordered structures. And if you have ordered structures, so there is no free rotation of that chain, and therefore you will have increase in TC values. So these are the factors which can affect the glass transition temperature. Plasticizer is very important parameters which can affect glass transition temperature. So now let's understand what is the plasticizer and how it will affect glass transition temperature. So the plasticizer is kind of this molecule which has low molar mass compound, and it has the high boiling point. So plasticizer is kind of the molecule which has the lower molecular mass and high boiling point, so that cannot evaporate at that working conditions from the polymers, and that's why we need to have the kind of the liquid which has the very high boiling point. So these are the things compounds. So suppose you have polymers, you have kind of polymer there. So this is your polymer. And if you add here, if you add plasticizer, so that depends on how much plasticizer you will add in that polymer. Based on that, that has effect on. So based on that, that effect on TZ values and mechanical properties. Mechanical properties. So what is happening here? Suppose we have polymers. So for this, if we have the polymer and that has W, W amount, or maybe W is the weight fraction. So if we add plasticizer in the polymer, so in that case we have some amount of the polymer and we have some amount of the plasticizer, right? So here the W is the weight fraction of polymer and W1 is the weight fraction of plasticizer. So if we have the weight fraction of polymer and here we have Tz. So here Tz is glass transition temperature of polymer and the Tz. So this is glass transition temperature of plasticizer. So using this formula, we can calculate what is the glass answer temperature of the mixture of the polymer and the plasticizer. So here we have 1 by Tg in MAM for the mixture, and we have W upon Tg and the 1 upon Tg1. So if we use this formula, so based on that, we will get the what is the glass transition temperature. So using the glass transfer temperature, you will decrease overall the glass transfer temperature of a polymer. And there, so using this formula, you will find out what is amount of the how the amount and the plasticizer affects overall the glass transfer temperature of the polymer. And based on that, we will change from a rigid. So if you add plasticizer, what will happen? So you can change polymer or maybe rigid polymer into elastic polymer. So if you add plasticizer, so based on that decrease in the glass transition temperature, the polymer becomes from rigid to the elastic kind of the polymers. Now let's understand with the example how that plasticizer change in the elastic in nature of the polymer and how that is used in product development. As we use this kind of the material, for example, the raincoat we use in raincoat, maybe the curve and maybe the this jacket kind of things. And so these kind of the materials are made of this polyvinyl chloride. So that is made of the PVC polymer. Since PVC polymer is very brittle in nature at the room temperature, because it has very high glass transition temperature, that is 354 Kelvin. So if you want to make very flexible, soft, soft material of that PVC, we need to add plasticizer from 32 to 40%. So these are the well-known polymers, diiso, diiso isonyl phthalate, DINP is, and the other is the dioctyl phthalate. So these plasticizers are commonly used at in industrial scales to make the flexible material of PVC. So now let's understand if how we what if we want to make the sensor based on the polymeric material. So how will we use plasticizer in sensor development? So in college lab, I developed PS sensor of the size of 150 micrometer. So for that, we use this kind of the composition of the material here. We have the 4% of the anophore. We have the potassium tetracis for chlorophenyl borate. We have the PVC is 31% and the dioctyl silicate TOS plasticizer. So if you just see the percentage here, so here PVC and the plasticizer. So the percentage of the plasticizer is 200%, double as compared to the PVC. So if you use at different percentage of plasticizer, so based on that you can make the flexible coating of that materials or maybe the sensor. So this is kind of the DOS plasticizer is there. So if you want to develop sensor, so you can consider this kind of the composition, or maybe you can vary the percentage of your plasticizer. So that depends on your the sensitivity of your sensor, or maybe the how flexible sensor you want to develop. And this is the important things. And further, we also develop a PS sensor of the size of here we develop a sensor of size of 25 micrometer. So in this sensor development, we have used PVC is 3% and the plastic size is 30%. So if you compare here, is this the 10 times concentration of plasticizer as compared to the PVC. So this is kind of NPOE plasticizer. So if you use this plasticizer, you can make very flexible kind of or elastic kind of the membrane so that we can be used in the sensing application. Now let's understand what is the effect of the copolymerization. So if we develop the polymers, we have different kind of the polymerization reactions happen. So here we have kind of those two kind of the monomers. So if you have two kind of the monomers, so based on that we have here there is the formation of homopolymers. So we because this is A type and this is the B type, so this is the homopolymer. However, these are copolymer. So if you have the homopolymers or maybe the copolymers, so in the copolymers we have the block kind of the polymers. We have the one kind of the polymer and then again another kind of the polymer. So this is the block polymer, or maybe there is the random polymers AB or and AABBB kind of the random polymerization reactions happens, or maybe there is the kind of the alternate polymers. So based on this, we can have the glass answer temperature. So we have conditions if these polymers are miscible. Suppose if you develop these polymers and if you're just mixing together, and if these polymers are miscible, in that case you will get the single glass transfer temperature. Maybe for example, so that this single glass transfer temperature is based on the glass transfer temperature of the monomer A. So here we have the monomer A and monomer B. Suppose the red one is A and the green one is B. So here glass answer temperature of A, and here WA is the kind of the weight fraction of A. So suppose from A monomer A and B you have the polymer of A and you have the polymer of B. So based on that, what is the glass transition temperature of the pure polymer of A, and WA is the weight fraction of this one, and TGB is equal to here. TGB is equal to what is the glass transfer temperature of polymer B kind of things, and what is the weight fraction of the polymer B. So using this formula, we can calculate what is the single glass transfer temperature. However, this second relation is more accurate as compared to the first one based on the experimental data. And this is called Fox equation, where we have 1 by Tg copolymer is equal to WA by TGA plus WB by TGB, where WA and WB are weight fraction. Weight fraction. And TGA and TGB are the glass transfer temperature of A and B. So this is the effect of the copolymerization happens. Sometimes what we do, we make the blending of the polymer. Suppose we have this polymer kind of A and polymer kind of B. And if you want to make kind of the specific kind of material which has certain mechanical properties, so for that, we blend this polymer. So if we blend these polymers, if using the polymer A and polymer B, if we mix together, so even that we will have such kind of the glass transition temperature. For example, if that polymer are miscible, so in that case we have the single glass transition temperature. So we can use either of the equation. And if is immiscible kind of the composition, then we'll have this two glass transition temperature, and we get the separately TGA and TGB. And if we have the partially miscible, so in this case we again have the different temperature. So this is about the blending of the polymers and the copolymerization of the polymers. And we have another very important factor, that is the molecular weight of the polymer. So using this equation, we can understand that what is effect of the molecular weight on the glass transition temperature. So here this glass transition temperature is equal to Tg infinite. So this Tg infinite means the molecular weight of the polymer at very high molecular weight. It's not is at high molecular weight. And here sigma is the density of the polymer, y is the number of the chain per, per chain, and here the theta is the contribution of the one chain into this free volume. Alpha F is the coefficient of the thermal expansion of free volume, and M is the number F is molecular weight. So here, based on this formula, if you want to understand what is the relation of Mn and this Tz, so we will get such kind of the things here, where we will have the reason where there is the situation happens where we have these values. So we in this range we will have the Tz is equal to the Tz infinite, where both are the, so at very high molecular weight, so this Tz, the glass answer temperature is equal to the glass answer temperature of infinite molecular weight. So here, so in this range, we have the variation of molecular weight. So if we increase molecular weight, so there is increase in glass transition temperature. So this range is important for us. So here, important for us, if you want to change molecular glass temperature with molecular weight, then we can just play with the molecular weight, and then we will have the different mechanical properties of the polymers. But here, these formula, so here this formula is only valid for molecular weight greater than 5,000. So this formula is only valid if we have molecular weight greater than 5, is more than 5,000. So what about if we have the less molecular weight or the lower molecular weight, the polymer? So what about, so how will we know for lower molecular weight or polymer? How easy it depends on molecular weight. So we need to know if we have a lower molecular weight, or maybe this molecular weight is less than 5,000. So how that easy gets affected. So for that, we need to understand this relation where if we want to understand this one for lower molecular weight polymer. Excuse me. For lower molecular weight polymer, for example, if molecular weight is less than 5,000, so in this case, if we want to know what is the effect on the TZ, so we will plot the graph between TZ versus log XC, where TZ is the glass transfer temperature, and here this scale is the log XC. So here XC is about the number of atoms in backbone. And based on that, if you want to understand how the glass temperature gets affected based on this number of atoms in the backbone. So we have the different three regions: region one, region two, and region three. So here the region first comes at very high chain where we have the, so at this particular, after this particular molecular weight, or maybe the number chain. So here in this range or region one, we have TZ is close to the TZ infinite. Right. So in the region one, there is some kind of situation happens where the glass transfer temperature is is close to the glass transfer temperature at high molecular weight. So this process happens if you have the Xc value where the this is Xc, that is the critical size or the number of the atoms in the chain. So if you want to understand how these values change for the different kind of the polymer. So here this one is for the PDMS. So in for the PDMS, this values is close to maybe 60. Sorry, so this is close to the 90. And here this value is close to 600. This value is close to the 600. So here XC values change from 90 to 600. So it depends on the flexibility of the backbone. So here the 90 is for the PDMS. And so because of the high flexibility of the backbone of the PDMS, the XC value is very, very less. And this is for the 600 for poly alpha methyl styrene. So based on the poly alpha methyl styrene, there is high XC values. So in the region 3, so if they in so at lower of the X values, so if you want to understand the Xc values is increasing, if you're increasing the rigidity in the chain. So from here to here, there is increase in rigidity in backbone. And in the region 3 and 2, we have the dependency of a TZ with the log Xc. So in the region 2, we have this relation. So here we have this TZ depends on the log X values. So this is all about the molecular weight and how this molecular weight depends on how glass temperature depends on the molecular weight, and this is a very important parameter. So, and in summary, so here's the Mn increases. So there is an increase in Tc values, and for high molecular weight, beyond the point, practically it remains unchanged. So this is talking about this range, and the branching increases, Tc decreases. So this is all about the factors affecting glass transition temperature. In next class, we will understand melting point of crys- crystalline polymers, and later on we will understand what are the relation between Tz and Tm. So we are going to understand what is the relation between Tz and Tm, and how we will design the material so that we will have a mechanical properties that depends on the values of Tz and Tm. Thank you very much. I'm looking forward to see you in the next class.